All right, so we need to talk about the orthogonality of the four subspaces. So first things first, we need to label our four subspaces on our picture here. So my claim is that we've already talked about some of these, and I'm going to assume that my matrix A, that's kind of going from the left side of my picture to the right side of my picture, is an M by N matrix. So if it's an M by N matrix, then the left-hand side of the picture has to be Rn, and the right-hand side of the picture has to be Rm. That's because if I'm going to multiply A by a vector x, right, then my vector x needs to be n by 1. The n's will tell me that I can do that multiplication, and the m by 1 is going to tell me about my result. So I've got my setup here. I've got A as an m by n matrix, goes from left to right. The left-hand side of this, we might remember, is called the domain. The right-hand side of this we call the codomain. We might remember some things about these, so we've labeled some of these in the past. All of the stuff here, the green stuff that goes to 0 under our operation, is the null space of A. Right, that's all the vectors that go to 0 under our matrix A. We might recognize that this yellow space here, I've kind of probably labeled this in a picture before. This is the row space of A. You might notice that the row space of A is actually the column space of A transpose. And then on the right-hand side of the picture here, I'm going to label these spaces. This blue space is going to be the null space of A transpose. And the red space is going to be the column space of A, which you might note is the row space of A transpose. So the thing that we're going to talk about right now is this right angle right here and the similar right angle over here. In order to do that, we need a little definition. So we want to say something like two subspaces. I'm going to call those V and W, are said to be orthogonal orthogonal I can spell, I promise, if any pair of vectors V, which is in V, and W, which is in W, have V dotted with W is equal to 0. So, in other words, two subspaces are perpendicular to one another, right, or orthogonal, if any vector in V is perpendicular to any vector in W. Should be noted that if they're subspaces, right, so special note here, 0 has to be in V and 0 has to be in W, right? My two subspaces are going to have to overlap at the 0 vector. So that's my picture here. That's why I've got 0 drawn in this corner. That is going to be an overlapping point between these two spaces. You might notice that that's got to be the only overlapping point, because if there was a vector that was in both of these two subspaces, W and V, it wouldn't be perpendicular to itself. And so we wouldn't have this orthogonality for any pair of vectors, right? Because we could pick, like say we had a vector U that was in both spaces, right? Then U is a vector in V and U is a vector in W. So U dotted with U had better be 0. That enforces that it's the 0 vector. All right, so that's one thing. Another little note here, I'm going to call this a definition too, although it's just an extension of the previous definition. So two subspaces V and W, which are, at this point here, I'm going to consider subsets of R, K, right? Subsets of some R to the K power or whatever, are called orthogonal complements if V is and W, oops, come on. So if V and W are orthogonal, surprisingly enough, and V, well, I need a way to put V and W together as spaces. So let me just say, and the dimension of V plus the dimension of W is equal to K. So they're orthogonal complements if they are themselves orthogonal, and also when you add up their dimensions, you get the dimension of the space they live in. You guys are familiar with some kind of orthogonal complements. So in R3, we might have a plane, right? That's a two-dimensional subspace, right? We're going to stick that, stick the zero vector in there someplace. And then we might have the normal line to that plane, right? So my two subspaces are here. That's like a vector or a subspace V. And here, this is a subspace W. And the only requirement for these to be orthogonal complements is that that W actually has to be the normal line to the plane here, V. So V is two-dimensional, W is one-dimensional. Any vector in the space then can be written as a vector in W plus a vector in, a vector in W plus a vector in V. So a vector in the plane will get you someplace out in the plane, and then run out along W to get the kind of height off the plane. So that's an example of orthogonal complements. In R2, we might have another example. So in R2, right, we've got two-dimensional space here, and we might have some line through 0 here. We might call that a subspace V. And then we just need a perpendicular line to V. So that'd be, this is W. And then you guys are used to doing some kind of like projection analysis, right? So we might think of, all right, so here's a vector in the space, right? So that's a vector in R2, and I can decompose that into a piece that's on the kind of V, I hesitate to say axis, but like along V, and then a chunk along W, and those things are going to be perpendicular to one another because the subspaces themselves were perpendicular to one another. This is like a pretty common thing for us to do in, like, say, a physics problem where we're setting a block on an inclined plane, and we want to have the component of, we'll like look at our gravitational attraction vector, and we'll have a component that's kind of running along the plane and a component that's perpendicular to the plane. That'd be kind of some uses for this. So all this to say, there's actually a pretty easy little result here. So let's take a look at an easy little result. So the easy little result that I'm going to claim is that the null space of A is perpendicular to the row space of A. So my claim is that this is pretty easy. In fact, I probably spent more time talking about definitions than it'll take to prove this. So my claim is N of A is orthogonal to row space of A. So in order to demonstrate this, I need to demonstrate that any vector in the null space is perpendicular to any vector in the row space. and then we're good, essentially. So here's what I'm going to do. I'm going to take my matrix A here, and I'm going to think about my matrix A as a bunch of rows. So I've got row 1 there, I've got row 2 here. I know how many rows there are going to be because my matrix is m by n. So there's going to be an Rm down here at the bottom. That's going to be my last row. And then I'm going to say, all right, I need a vector in the null space. So let's scoot this down a little bit and say, all right, let's let x be in the null space of A. And our kind of off here in the margin, I'm thinking I want to show that x is perpendicular to any vector in the row space. So I'm going to call that R, I guess, which is in the row space of A. All right, so that's kind of the thing I'm after, right? So since x is in the null space of A, right? So since x is in the null space of A, if I take my matrix A and multiply it by my vector x, I know what I get. I get the 0 vector, right? That's what it means to be in the null space of A. So let me write that down kind of carefully here. So I'm going to write the 0 vector down here. Okay. And I'm going to analyze this using the row picture. So I'm going to say here, actually, I'm going to put more thought at this. So I'm going to say here that we're going to think row picture. Okay, so we're going to think the row picture, and we're going to say, all right, this means that row 1 dotted with x has to be 0. That's the first line of this, essentially, right? As I pick x up, twist, and drop on the row, I'm going to do R1 dotted with x has to be this top 0. That's my first equation. Second equation is going to be R2 dotted with x is equal to 0. And then we're going to get all the way down to Rm dotted with x is equal to 0. Okay, so that's something I now know. So I'm going to say, all right, let's let R be in the row space of A. Okay, so that's me kind of thinking back to what I want to show. So if R is in the row space of A, since the row space of A is the span of the rows of A, this means R in the row space of A is some linear combination of the first row, the second row, and on out to the mth row, right? So because it's in the row space, it's a member of the span of the rows of A, which means that it can be expressed as a linear combination of the rows of A. Now what we're going to do is we're going to say we're going to consider x dotted with R. So this is going to be x dotted with this sum here. So I'm going to save myself some wrist cramping. And I'm going to drop that in there. And that's going to equal A1x dotted with R1 plus A2x dotted with R2 plus AM x dotted with Rm, which is equal to A1 times 0 plus A2 times 0, and so on. Why do I know that these are all 0? Well, earlier, right, we considered the row pictures. So I'm taking this information here, So I took this information and we stuffed it in right there. And that got us to all of these quantities being 0. And then we can do a little simplification here. So that's 0 plus 0 plus 0, so that gets me 0. And that's enough. So any vector x in the null space of A is perpendicular to, or orthogonal. There's a slight distinction between those two words, but it's not like incredibly important right now. So any vector x in the null space of A is perpendicular to any vector r in the row space of A. So what that means is that I can go up here to my picture and I can put in this little perpendicular guy. So I know now the null space is perpendicular to the row space, and the row space is the column space of A transpose. Now, I'm going to apply a kind of dirty trick to you. So that dirty trick is this. Let me write this out. So our claim, just proven, amounts to n of A is orthogonal to row of A. Now, I didn't use anything special about the matrix A. So what that means is we can apply this to A transpose. So essentially, I proved that the null space of any matrix is orthogonal to the row space of that same matrix. So I can just swap in A transpose for the A's here. That's not me claiming that A is equal to A transpose. That's just me saying the null space of a matrix is perpendicular, the null space of a matrix is orthogonal to the row space of that same matrix. So now I'm going to say, all right, so that applies to A transpose because A transpose is a matrix. And what that means is the null space of A transpose is orthogonal to the row space of A transpose. But the row space of A transpose is the column space of A. This thing, the null space of A transpose, is often called the left null space. I'm going to continue to call it the null space of A transpose because I think that most students are confused by the idea of the left null space. So the null space of A is orthogonal to the row space of A transpose, but the row space of A transpose is the column space of A. And what that means is that I can go back up to my picture here and I get to put in this perpendicular essentially for free, which is really cool. I just got that freely. It just came out of nowhere. There is one thing to note here. Because of the counting theorem, we now actually know that these spaces are orthogonal complements to one another. That's straight up from the counting theorem. So from the fact that columns in a matrix must either be pivot columns or free columns, and the number of pivot columns is the dimension of the column space, or the dimension of the row space, and the number of free columns is the dimension of the null space, I get for free that those things are orthogonal complements. So they add up to the whole space, which is really neat. There's one thing I want to improve about this picture. I know from the counting theorem that the dimension of the yellow box here, right? This has a dimension of the row space of A, right? Which is equal to the rank of the matrix A. This space here has that the dimension of the null space of A is equal to n minus the rank of A. Right? The nullity of a matrix is essentially the number of columns there were in the matrix minus how many of them were pivot columns, right? That's straight up how many free columns are there. So on this right-hand side now, I have some little tidbits that I can add. I know that the dimension of this space, so the dimension of the column space of A, is also equal to the rank of A. That's why the orange or the yellow box over here and the red box over here are the same size. Now, this blue box down here, the dimension of the null space of A transpose, oops, that got away from me. So down here, the dimension of the null space of A transpose is equal to M minus the rank of A. So that space is possibly a different size than the green space. So I think it would be good if we added a little padding down here. So I'm just going to grab this text here. I'm going to scoot this down a little bit. And then I'm going to go ahead and add that little bit of padding. And this is essentially me saying, look, there may be a size difference between the left null space's size and the right null space's size, but there will not be a size difference between the row space of A and the column space of A. Those have to be the same size. They both have to be the dimension, they both have to have a dimension equal to the rank of the matrix. Hope this has been helpful. Thank you guys for watching. Much appreciated.